Anyway, these are sort of a collection of things that are part of GSAS-II and you may find interesting. Constraints and restraints. Now, constraints and restraints are two different things. People sometimes use those two phrases interchangeably, but they're really not. A constraint is something that reduces the number of parameters. Okay? Think about it that way. And there's sort of three different kinds of them. And there's, first of all, some fairly obvious symmetry constraints. If you've got an atom that's on a special position where the X and Y values have to be the same, there's a constraint that makes the two of them the same. So that's a constraint. Another sort of constraint is the kind of situations where if you have two different kinds of atoms occupying the same site in a crystal structure, and you want their site fractions to sum to 1. That's a constraint that you would put in. If you didn't put it in there, they could go who knows where, okay? And the third kind is a sort of more specialized arrangement of something called rigid bodies, where instead of describing the coordinates of each of the atoms in the rigid body individually as X, Y, Z, and a bunch of temperature factors, you link them together as an object that moves together with much fewer parameters, typically just simply a coordinate for the entire object for the rigid body. And then three things that would describe its orientation. Or, and this is the case of a protein, and here's a little bit of the protein chain, amino acid chain. And this happens to be phenylalanine. There's the phenyl ring, carbon, alpha carbon, oxygen, and then a linkage is here, and the other linkage is off the, sort of sorted out off the nitrogen that way. So you could describe this thing as a rigid body by having a translation that translates the alpha carbon to its appropriate point in the chain. You then have a rotation of the entire group around some vector. And I'll get to what this means in a minute. And then you have three possible rotations of around three bonds. Carbon-carbon bond, this carbon-carbon bond, and then that carbon-carbon bond. So this one simply rotates the ring around. This one takes the ring and so switches around like that, and so forth. So what's this cube? In fact, all these guys are described using the same sort of thing. This is where it gets weird. They're quaternions. They're an invention of a person named Sir William Rowan Hamilton in 1843. And he actually had the bright idea about these things while he was walking across this bridge in Dublin. He had a bright idea and he scratched the equation, the relevant equation in stone at the top as a bit of graffiti. And so someone said, yes, it says here, cut it out on the stone of the bridge. So he would remember it, I guess. So someone put up this little plaque that says, here is where he invented this thing. And there's sort of mixed reviews about these things, because here is a comment about them by Lord Kelvin about the time, who said he's done really good work, but these things are really kind of odd, basically. And by the way, this Hamilton is the same Hamilton as we know from that equation, the Hamiltonian. That is that Hamilton. Right, John. Okay. So what are they? Well, you know about real and imaginary numbers, where you have a real and then there's I, an imaginary number. Imagine the same thing, except you're going to have three imaginary numbers and one real, so it's 4. So it's a real and then 3 imaginary components. is a normalization. Some of the indices equal to 1. You can define a rotation vector in which are the components are about the imaginary bits. And then the rotation itself can be obtained from the value of R that way. Also a little bit of water. And you can multiply quaternions together, which means one rotation followed by another rotation. As you can imagine, they don't commute because if you do in the opposite order, you wind up in a different place. So they don't commute. And this is how you would actually apply a quaternion to a vector. So you actually do quaternion times the vector times the inverse of the quaternion to make the rotation. Where are they used? Well, every time you move your mouse to turn your molecule around in a structure drawing, it uses quaternions to do the rotation. So as you move the mouse, it establishes where the vector is and how much you rotate. It's also used for flight control systems and fighter planes, and probably in commercial planes too, because it's a lot easier to translate. They do stick to what happens to all control surfaces on an airplane.
It's also used in 3D scanners.
Sorry?
It's also used in 3D scanning. 3D scanning? That's also used for that.
Yeah.
Friend of mine's an engineer, so.
They also use them in video games.
Oh.
Okay. But if you want to write video games, you got to learn about quaternions. And the reason is there's no lockup when in Eulerian angles when omega is 0, and so omega and phi are locked together at the same parallel. This doesn't happen. Weird but cool. Restraints are additional observations. So you have a powder pattern, say, with number of peaks and profile points, and it's not enough information to be able to restrict the crystal structure to what it is. So you add in extra terms that restrict things like bond lengths and angles. Those are additional observations on the crystal structure. And so go into the least squares as additional observations. You have to take derivatives of them, and they go into the matrix. And there's all sorts of them that are possible. And in protein structures, there may be thousands of these things on the bond length and the angles, planes are flat. They just so it adds to the data. Okay, different subject. We heard about this yesterday as a big box modeling. And so what I want to do is just basically show you that there's a GSAS-II interface to it. And it looks like this. And it has ways to read in the data, set up the stuff for running RMC profiles, which runs as a separate program. This actually was written in Fortran. And then as it runs, which could be hours and days, you can pull out intermediate information and see what the progress of your calculation is. And so that's the kind of stuff that's displayed here. You can tell what the progress of the calculation is. You may even want to kill it if it's going astray. Okay. So here's a result. This is sulfur hexafluoride. This is part of their tutorial. So it's a real simple little cubic structure, body-centered cubic. The problem is that if you do a refinement, calculate sulfur fluorine distance, it's too short. And the reason why it's too short is because these darn things simply run into each other in crystal structure. So they have to sort of adjust themselves like this. And so the big box simulation allows you to allows it to relax in that way of displacing the atoms, the fluorine atoms in particular, away from their idealized position in the crystal structure. So here's what the anisotropic refinement would be for SF6 from powder diffraction data, the repel refinement. Here's the RMC profiles simulation, which was originally a 10 by 10 by 10 block of atoms. The atoms were then all folded back into a single unit cell, so you could see how they all overlapped on each other. And the distribution of them is pretty good and well matched to the anisotropic temperature factors. But the actual distances are not too short anymore. Okay. Related subject, the so-called small box model. And there's this routine which is available out on the web, written by, and you can't read this, but it's by the folks at the University of Utah, which you give it a crystal structure, and it will then tell you what the mode displacements of the atoms are, according to the symmetry and how the subsymmetry occurs with it. And it's a long, sort of tedious process to use this thing because you have to feed it a CIV file, respond to it. It goes away, makes another calculation, comes back with yet another window. You respond to that, and it goes back and forth about 4 or 5 times. And it comes back with a CIV file with the stuff that you want to know. So I wrote an interface that works across the web from GSAS-II to ISO to store it. And it comes back with the stuff that you actually need to do the calculation. And what comes back then is basically a set of irreducible representations. Don't worry about that buzzword. It's basically symmetry, based on the symmetry of the thing. But what it is how a group of atoms would move according to some distortion. It's a little bit like finding vibrational modes in something. The same kind of idea. So you get these, and if I go on to the next slide, mouse backwards. There we go. So in this particular case, this is lanthanum manganese oxide. It's a perovskite, and it looks like that. And so the question is, if you begin with the high symmetry version of this, which is tetragonal, something like that, and this winds up being orthorhombic, is that how did it get there through a phase transition? And you can do that by working out what these mode displacements are and simply watch them as a function of temperature. See what they do. And so it creates the atom position constraints with this interface. And here they are listed. You can't read this from where you are, but this gives you the little equations for the atom positions in PDF fit 2 nomenclature so that you can actually do that, run PDF fit 2, do the work. And you feed it for data, show here, a bunch of PDFs. And you can then, in this particular case, it was, I don't know, 60 or 70 of these PDFs that were measured, something like that. Can't remember exactly, as a function of temperature. And so if you watch what the modes do as a function of temperature, you can see that at some point they collapse. And that's where the phase change is. And you can notice which ones, some of them don't change hardly at all through the phase transition, and some of them go through rather dramatic changes through the phase transition. And you can then look at and see what happens, whereas in this particular case, it was a rocking of the manganese 6 oxygen onto here. Just tipped in a particular way. You can actually see it. Okay. In commensurate structures, now something even more different, but kind of linked, because in a sense, this is also what you're seeing. So what's going on in incommensurate structure? One of the things that shocked me about incommensurate structures is how often it shows up in extremely simple materials. Sodium carbonate. Who would have thunk it? Okay. Simple material, but it's incommensurate at room temperature. You don't have to do anything to make it do this. This is a single crystal diffraction pattern of it. It's a slice on HOL. And you notice, if you look at it very carefully, those spots just don't line up. They come close, but they don't. And that's what makes it incommensurate. And there's a modulation vector that describes how these things are incommensurate. And in this case, it's roughly a sixth, 0, a third, but not quite. If it was exact, you could call it commensurate, but it isn't, so it's not. So H reflection then has 4 indices. The conventional HKL, and then there's a fourth one, M, which, if non-zero, means it's part of the superlattice. If it's 0, it's a sublattice reflection. It's a little hard to tell from this picture, but generally the superlattice reflections are much weaker than sublattice. There. This is a powder pattern of sodium carbonate taken at room temperature on 11 p.m. And you can't tell which ones are which, but based on the sublattice, there's way too many reflections. It's because probably 2/3 of the peaks in here are superlattice reflections, something like that. And so this was fit through a refinement of a 4-dimensional object, which is the XYZ, and then there's an additional 4th dimension for the modulation. And it included 2 orders of harmonics for the atom positions. I'll talk about that in a second. Now, as you can see here, there's lots of things going on here. First of all, this is showing the modulation as if it was as a function of time. It isn't, but I've displayed it that way, okay? And you can see what's going on here is that the sodium atoms are shifting back and forth at the same time as the carbonates are doing a funny little dance in the middle. This is the 4-dimensional Fourier map showing the peaks in the Fourier map shifting back and forth along the prism. And if you do a slice through this as a function of y through one of the sodium positions, and this way in that 4th tau dimension, you can see the oscillation in the sodium position along y. That's basically a 4-dimensional Fourier map. Here's another view of the same thing. But this is expanded out so that it's 3 unit cells this way, which is full modulation distance, basically along the c-axis. And that way is along A. And you can see the modulation in in the sodium atom positions is they go up and down in a wave, and you can see how the carbonate atoms groups rotate along with it. Okay. The movie was made with GSAS-II. There's a routine for doing that. Okay. These things have space group symbols. And the space group symbol is interpreted by GSAS-II. It's not a look up in a big table someplace. It actually takes this thing apart and says, okay, what's all these components, and puts it together. So this piece here is the space group symbol, C2/m. This tells what the components are for the modulation vector. It doesn't say what the numbers are, but it says alpha, 0, gamma. And then this thing is a translation component on the two modulation vectors. It tells you whether there's an offset or not. A little bit like a glide. But not quite. So the operators then have 4 pieces, an X, Y, and Z, and then this fourth dimensional offset. So that S that's there is where this little half comes from. Okay. There we go. The model for the modulation itself, yes, a Fourier series. That's the absolute logical thing to choose. Simple oscillations. And there may be more than one of them superposed on each other, and they have orders. So it's either full or half, quarter, or whatever. But there's also a possibility of having other things like zigzags, sawtooths, and so-called block waves, square waves. Because that's sometimes what happens with the atoms. They just go like that without doing this kind of thing. And so the positions can do that. The temperature factors are restricted to basically Fourier series. Yes. 5 minutes? Oh boy. Okay. I'll speed it up. Anyway, you can see this. Now, here's the one thing that GSAS doesn't do. It only does 3+1, which is 4 dimensions. It doesn't do 5 or 6. And the reason is because there's an awful lot of space groups possible for 3+1, 4,700 of them. But for 3+2, 200,000 of them. And for 3+3, there's 28 million of them. But the actual fact is you only find a handful of them. So I said, not worth the hassle, not bother. You're not allowed to have these weird X-type space groups. If you don't know what I mean, don't worry about it. But you'll find them in SID files. Okay. And I'm going to skip that. Because I want to get onto this. And I'll do this quickly but there's a really interesting story at the end of this. Charge flipping, I sort of brushed through this rather quickly when I showed the algorithm, showed the code. But the steps are you start with a set of reflections, fill them out to a sphere. The origin is here in the center of the sphere. And what you have to do is shift the origin down to there because of the nature of Python. And you fill it out as a box. You then expand the box so you have a bigger box. And the reason for doing this is you want as many points in here for the reflection set as you have points in the map that you're going to make when you do the Fourier transform. That's how you do the fast Fourier transforms. So that's why this is bigger. And then the algorithm is you assign everything in here random phases. Do the fast Fourier transform, you get a map that might look like that. You do the charge flip to get rid of the red negatives through here. Do an inverse Fourier transform take the phases out of here, apply them to that, and go back. And just go round and round. This is a cyclic calculation. And I showed you that the other day. This is the example of sucrose powder, and you index it, and I'm going to skip that. And so here's the crystal structure that comes out of the charge flipping for sucrose, where it starts off with a residual of about 40%, drops down to something like 17, and there's 46 peaks in the mat. And since this is P21, it's twice that of sucrose, which is C12H22O11. So you should get 46 peaks. Half of the, how many? 22 oxygens and 24 carbon atoms. And when you look at the list of the peaks, the top 22 of them are oxygen, there's a break, and the rest of them are carbon. Simple. So you know what they are. You assemble a molecule, and there's the crystal structure. And you do the Rietveld refinement after that. Now, this is the interesting part. And this is the thing that I really want to talk about as a sort of closeout of what I've done here. If you track the phases of 5 reflections, and it doesn't matter what 5, you just pick 5, they will do something like this. Some of them pretty much are the same all the way through the cycles of, this is 10,000 cycles of charge flip, but some of the other ones will simply just bounce all over creation. And this did not solve. Here's one that solved right there. It sort of snaps into a position, and then there's some oscillations, true, but it's fixed into a solution or a set of solutions. And if you look at this spot in detail, you can sort of see it on this side wandering around, and then suddenly it just locks in. There was another one. This one solved here. So you get this pattern of uniformity after that. So what's going on? Well, chaos mathematics. Anybody know about that? Who knows about chaos? I mean, apart from your life. Well, when you read about it, you'll see all these sort of buzzwords. Strange attractors, Cantor dust, the butterfly effect, that's a real famous one. The so-called basin of attraction. Is any of this stuff relevant to charge flipping? Well, it turns out it really is awfully suggestive. First of all, you have a cyclic algorithm, and in successive iteration, it wanders all over the place, and then you suddenly get a stable solution. It is chaotic, but it's deterministic. In other words, if you start with the same set of phases, you will always get to the same charge flipping solution. Always, every single time. It always follows the same path. But if you shift that starting position, it will go to a completely different solution. I mean, it looks like the same structure, but it's been shifted or inverted or something like that. Or it may not have solved. This thing is hyperdimensionality because there's 7,600 reflections in this case. And so there's 7,600 dimensions in the problem. And there's no symmetry used in charge flipping. There's infinite phase possibilities for all the possible configurations. And similarly, there's a smaller infinity of solutions, but it's still an infinity of solutions. And so this is what's known as Cantor dust, I think, if I read that stuff correctly. And here's a sort of simple two-dimensional thing where you have the solutions wandering around through these paths through this sort of little loop, a little bit like a mini charge flip. And so there's oscillation in the phases, and you saw that in those plots where the phase would simply bounce up and down from one point to the other after the solution was found. And that has to do with the nature of the so-called strange attractors. So the solutions to charge flipping are in fact strange attractors in this nomenclature. The next question is that if you shift the starting position a little bit, how close does it come back to the starting position? Or does it simply go off somewhere else? And that's got to do with basis of attraction. And of course, the last question is, does it really matter? Well, yes, it does, because in a sense, this is how you can understand how charge flipping is actually working. Because it's not magic, it's chaos. Okay, and with that, thank you.